in the 40s, the physicists went to the Manhattan Project, even if they were doing other things. That was the place to be. And so now AI is the same thing, and basically set OpenAI as that place. So maybe we don't need a public sector organized Manhattan Project, but it can be OpenAI.
Joining us for this episode is Dan Roberts, a former Sequoia AI fellow who recently joined OpenAI as a researcher. This episode was recorded on Dan's second to last day at Sequoia before he knew that he would go on to become a core contributor to O1, also known as Strawberry. Dan is a quantum physicist who did undergraduate research on invisibility cloaks before getting a PhD at MIT and doing his postdoc at the legendary Princeton IAS. Dan has researched and written extensively about the intersection of physics and AI. There are two main things we hope to learn from Dan in this episode. First, what can physics teach us about AI? What are the physical limits on an intelligence explosion and the limits of scaling laws? And how can we ever hope to understand neural nets? And second, what can AI teach us about physics and math and how the world works?
Thank you so much for joining us today, Dan.
Thanks. Delighted to be here on my probably second to last day at Sequoia, depending on when this airs and how you're going to talk about it.
You will always be part of the Sequoia family, Dan.
Thanks. I appreciate it.
Maybe just to get started, tell us a little bit about who is Dan. You have a fascinating backstory. I think you worked on invisibility cloaks back in college. Like, what led you to become a theoretical physicist in the first place?
Yeah, I think, and this is my stock answer at this point, but I think it's true. I was just an annoying 3-year-old who never grew up. I asked why all the time, curious, how does everything work? I have a 19-month at home right now, and I can see the way he followed the washing machine repairman around and had to look inside the washing machine. So I think I just kept that going. And when you're more quantitatively oriented than not, rather than going to philosophy, I think you sort of veer into physics, and that was sort of what interests me. How does the world work? What is all this other stuff that's out there? The question that you didn't ask, but maybe I'll just answer it ahead of time. The sort of inward-facing stuff felt less quantitative and more in the realm of the humanities. So what is all this stuff? That's pretty physicsy. What am I? Who am I? What does it mean to be me? That felt not very sciencey at all. But with AI, it sort of seems like we can think about both what does it mean to be intelligent and also what is all this other stuff in sort of some of the same frameworks. And so that's been very exciting for me.
So we should be trying to recruit your 19-month-old right now, is what you're saying.
Oh, yeah, absolutely. He's got his, he grew out of one of his Sequoia onesie, but he fits into a Sequoia toddler t-shirt now. And so he definitely is ready to be a future founder. I
guess, at what point did you know that you wanted to think about AI? At what point did that switch start to flip?
Yeah, so I think like many people, when I discovered computers, I wanted to understand how they worked and how to program them. In undergrad, I took an AI class, and it was very much good old-fashioned AI. A lot of the ideas in that class actually are coming back to be relevant, but at the time, it seemed not very practical. It was a lot of, if this happens, do that, and there was also some game playing there that was sort of interesting. It was very algorithmic, but it didn't seem related to what it means to be intelligent.
Can we just pick up on that real quick? What do you think it means to be intelligent?
That's a great question.
I can see wheels turning.
Yeah, well, this is one of those questions where I don't have a stock answer, but I think it's important to not say nonsense. One of the things that's exciting to me about AI is the ability to have systems that do what humans do, and to be able to understand them from how, what are the lines of Python that cause that system to do something, to trace that through and understand what are the outputs, and, how the system can see and classify what it means, what is a cat, what is not a cat, or can write poetry, and it's just a few lines of code. Whereas if you're trying to study humans and ask what does it mean for humans to be intelligent, you have to go from biology through neuroscience through psychology up to other higher level versions of ways of approaching this question. And so I think maybe a nice answer for intelligence, at least the things that are interesting to me, is the things that humans do. And then now, if you pull back the answer that I just said a second ago, that's how I connect it to AI. AI is taking pieces of what humans do, and we're understanding at least an example that's kind of simple and easy to study that we might use to understand better what it is that humans do.
So Dan, you mentioned when you were studying AI in college, there's a lot of what sounds like kind of hard-coded logic and brute
Yes.
force type approaches.
Yeah.
Was there a moment that kind of clicked for you of like, oh, okay, this is different? Was there a key result or a moment where it was like, okay, we're going bigger places than kind of the if this then that logic of the past?
Yeah, actually, it didn't click. I sort of wrote it off, and it would be great. It'd be great if there was a separation between like 10 years between then and the next thing that I'm going to say. But actually, the writing off maybe lasted a year or two, because then I went to the UK for the first part of grad school. I spent a very long time in grad school, and I discovered machine learning and a more statistical approach to artificial intelligence, where you have a bunch of examples of large amounts of data, or at the time, maybe we wouldn't have said large amounts of data, but we would have said, you have data examples of a task that you want to perform, and I mean, there's different ways that machine learning works, but you write down a very flexible algorithm that can adapt to these examples and start to perform in a way similar to the examples that you have, and that approach borrows a lot from physics. It also, at the time I started, so graduated college in 2009, discovered machine learning in 2010, 2011. 2012 is the big year for deep learning. And so, there's not a big separation here between write-off and rediscovery. But I think, and machine learning clearly existed in 2009. It just wasn't related to the class that I took. But this approach made a lot of sense to me. And it started to have, I got lucky in that it started to have real progress and seemed to fit in a framework that I understood scientifically. And I got very excited about it.
Why do you think there are so many people who come from a similar background or similar path to you? Like a lot of ex-physicists and working on AI. Like, is that a coincidence? Is that herd behavior, or do you think there's something that makes physicists particularly well suited to understanding AI?
I think the answer is yes to all the ways
all the above.
Physicists infiltrate lots of different subjects, and we get parodied about the way that we go about trying to use our hammers to attack all these things that may or may not be nails. Throughout history, there are a lot of times that physicists have contributed to things that look like machine learning. I think in the near term, the path that physicists used to take when they didn't remain in academia often was going into quantitative finance, then data science, and I think machine learning was its realization in industry was exciting, because it's something that feels a lot like actual physics and is working towards a problem that's very interesting and exciting for a lot of people. You're doing this podcast because you're excited about AI. Everyone's excited about AI, and it in many ways it's a research problem that feels a lot like the physics that people were doing. But I think the methods of physics actually are different from the methods of traditional computer science, and very well suited for studying large-scale machine learning that we use to work on AI. There's traditionally physics involves a lot of interplay between theory and experiment. You come up with some sort of model that you have some sort of theoretical intuition about, then you go do a bunch of experiments and you validate that model or not, and then there's this tight feedback loop between collecting data, coming up with theories, coming up with toy models, understanding moves forward by that, and we get these really nice explanatory theories. And I think the way that big deep learning systems work, you have this tight feedback loop where you can do a number of experiments. The sort of math that we use is very well suited to the math that a lot of physicists are familiar with, and so I think it's very natural for a lot of physicists to work on this. And those tools, a number of them differ from sort of the traditional, at least theoretical computer science and theoretical machine learning tools for studying the theoretical side of machine learning, and maybe also differentiation between just being an awesome engineer and also being a scientist. And there's tools from doing science that are helpful in studying these systems.
Dan, you wrote this, what I thought was a beautiful article, Black Holes and the Intelligence Explosion. And in there, you talk about this concept of sort of the microscopic point of view and then the system level point of view, and how physics really equips people to think about the system level point of view. And that has a sort of complementary benefit to understanding these systems. Can you just take a minute and kind of explain sort of microscopic versus system level and how the physics influence helps to understand the system level?
Sure. So let me start with an analogy that I think is like very, goes even further than an analogy. But going back, what year is it? Maybe like 200 years or so. There was around the time of the Industrial Revolution, there was steam engines and steam power, and a lot of technology that resulted from this and ultimately powered industrialization. And in the beginning, there was a lot of engineering of these steam engines, and there was this high-level theory of how this worked called thermodynamics, where, and I imagine everyone's seen this in high school, perhaps, where, there's the ideal gas law that tells you that there's some relationship between pressure at volume and temperature. And, these are very macro level things. Like, you can buy a thermometer. You can also, like, measure the volume of your room. And you can buy a barometer as well. Maybe people don't, or look up on the weather report. But, these are things these are like measurements that we use and we talk about. But then underlying this, and it took us a bit later to like validate this and understand it, there's the notion of atoms and molecules, the air molecules bouncing around. And somehow we now understand that those air molecules give rise to things like temperature and pressure and volume, I guess, is easier to understand. The gases, the molecules are confined to room. But there's a precise way in which you can start with a statistical understanding of those molecules and derive thermodynamics, like derive the ideal gas law from it. And you can go further than that, derive, that it's ideal because it's wrong, it's just a toy model, but there are corrections to it, and you can sort of understand, from the microscopic perspective, which is the molecules, which we don't really interact with. We don't see them, we don't interact with them on a day-to-day basis, but their statistical aggregate properties give rise to sort of this behavior that we do see at the macro scale. And part of to get to your question, I think there's a similar thing going on with deep learning systems. And I wrote a book with Shoyeda and Boris Hannen on how to apply these sorts of ideas to deep learning, in at least in an initial framework that allows you to start doing this in an initial way. And to answer your question, the sort of micro perspective is you have neurons and weights and biases, and we can talk about in detail how that works. But when people think of the architecture, there's some very specific, some people say circuits, there's specific ways in which these things, there's an input signal, which might be an image or text, and then there's many parameters, and it's very simple to write down. It's not that many lines of code, even taking into account the machine learning libraries, but it's like a very simple set of equations, but there's a lot of weights, there's a lot of numbers that you have to know in order to get it to do something. And that's sort of that's like the molecules perspective. And then there's like the macro perspective, which is, well, what did it do? Did it produce a poem? Did it solve a math problem? How do we go from those weights and biases to that macro perspective? And so for statistical physics to thermodynamics, we understand that completely. And you could imagine trying to do the same sort of thing, literally applying the same sorts of methods to understand it. How does the underlying micro statistical behavior of these models lead to the sort of macro, or as you said, system level perspective.
Dan, maybe speaking of scaling laws, and I think you were at our event, AI Ascent. Andre Karpathy mentioned that current AI systems are like 5 or 6 orders of magnitude off in efficiency compared to biological neural nets.
Yep.
Like, how do you think about that? Do you think scaling laws get us there? Just combination of scaling laws plus hardware getting more efficient, or like, do you think that there's kind of big step function leaps that need to come in research?
There's maybe 2 things that could be meant here. One is that the way humans seem to work at a similar scale to AI systems is much more efficient. We don't need to see trillions of tokens before we speak. We see a much my toddler is already starting to speak in sentences, and he's been exposed to far less tokens than a typical large language model. And so there's some sort of disconnect between human efficiency at learning and what large language models do. Of course, they're very different systems. They're designed, the way in which they learn is right now very different. And so in some sense, that's to be expected. So there's this gap here that you could imagine bridging. There's another thing that I think is not what you meant, but I think is sort of the thing to answer about with respect to scaling laws, which is, and I talked about this a bit in the article, but lots of people seem to talk about this, which is, what is the final GPT? There's GPT-4 right now, and it could be other companies as well, but since I'm going to join OpenAI, let me represent my new company, right? So is it going to be 6? Is it going to be 7? At some point, right, if assuming we have to scale things up, there are things that are going to break, whether they're economic, we're going to run out of, we're going to try to train a model that's larger than the world's GDP or GWP, however the D works for the world. And or we're going to run out of, we're not going to be able to produce enough GPUs, or we're not going to be able to put, it's going to cover the surface of the earth. A lot of these things are going to break down at some point, and so probably the economic one happens first. So how many more iterations do we get before we run out of actually being able to scale practically, and where does that get us? And then I think to tie those two perspectives together, there's so scaling on its own, and of course it's impossible to disentangle this because people are making things more efficient. But there's you could imagine there's take literally what GPT-2 was, which was the initial big model, and keep scaling it up. Is that going to get us to some super different, exciting, economically power, or however you want to define what the end state of AI research and AI startups and AI in industry is? So. Or do we need lots of new exciting ideas? And again, of course, you can't really disentangle these, but I think the general scaling hypothesis is that it's just the scaling and it's not the ideas that matter. Whereas the how do we get to efficient like humans, I think requires non-trivial ideas. And to answer your question, the reason I'm excited about joining OpenAI is that I think there is high leverage to be had in the ideas, in going beyond scaling, and that we will need that in order to get to the next steps. And I have no idea what I'll be working on, but when this airs, I guess I will know what I'm working on. But that's what's really exciting to me.
Yeah.
Dan, is there almost like a pendulum that swings back and forth between scale and ideas in terms of how people apply their efforts in the world of AI? Like Transformers came out, great idea. Since then, we've largely been in this race to scale. It feels like things are starting to asymptote for a bunch of practical reasons that you mentioned. Is the pendulum swinging back toward ideas as the currency? It's less now about who can, have the biggest GPU cluster and more about finding new architectural breakthroughs, whether that's, reasoning or something else?
Yeah, that's a really great question. I think there's this article by Richard Sutton called "The Bitter Lesson," not the bitter pill, and it basically gives the argument that that ideas aren't important, that scale is what you need, and that all the ideas are always trumped by scaling things up. And I mean that says a bunch of things, but maybe that's a high level takeaway. And there's a sense of this where there are a lot of interesting ideas that came out in the 80s and 90s that people didn't really have scale to explore. And then I remember when, after AlphaGo and DeepMind was writing a lot of papers, people were rediscovering those papers and re-implementing them in deep learning systems. But this was sort of still before people realized, no, the thing that you need to do is scale up. And even now with transformers, people are exploring other architectures, or even simpler architectures that we knew before, that seem to be able to, there's a notion, maybe scaling laws don't come from, as long as the architecture isn't sick in some way, they come from sort of the underlying data process and having large amounts of data, rather than from having a special idea. I think the real answer is that there's a balance between the two, that scale is hugely important, and maybe it was just not understood how important, and we also didn't have the resources to scale things up at various times. The things that have to go into producing these GPU clusters that are producing these models are, you guys know this as well, that there's a lot of parts along the supply chain or along the product chain, whatever, you actually call it, in order to make those things happen and deploy them. And even, the way GPUs were originally, they've now co-evolved to be well suited for these models. And the reason, in some sense, you can think of transformers was a good idea was because it was designed to be well suited to train on the systems that we had at the time. And so sure, these other architectures could do it at an ideal scientific level, but at a practical level, it was important to get something that was able to reach that scale. So I think if you brought in ideas to be that sort of thing that's married with scale in some way, then I still think ultimately, someone came up with the idea of deep learning. That was an important idea. There's Pitts and McCullough came up with the original idea for the neuron, and then there's lots of Rosenblatt came up with the original perceptron, and there's a lot of people from going back 80 or so years of people just making important discoveries that were ideas that contribute. So I think it's both, but it's easy to see how if you get to apply. If you're bottlenecked and then all of a sudden you get to apply, if you're bottlenecked, people think about ideas. And then if you unlock a new capacity of scale somehow, then you just see a huge set of results. And it seems like scale is super important. And I really think it's more of a synergy between the two.
Maybe on the topic of the race to scale, Dan, you mentioned kind of just the economic constraints and realities, which I guess are more practically a ceiling in the private sector. You also mentioned the Manhattan Project earlier in terms of things that physicists have been involved with. Do you think we need a Manhattan Project style thing for AI, at the nation state or at the international level?
Well, one thing I can say is that part of the process that led me to OpenAI is I was talking with your partner, Sean McGuire, who brought me to Sequoia in the first place, and trying to figure out, is there a startup that makes sense for me to work on that has the right mix of sort of scientific questions, research questions, and also as a business. And I think it was Sean that said, and I don't mean the analogy in terms of the impact of, in terms of the negative impact of what you might think of the Manhattan Project, but just in terms of the scale and the organization. He said, in the 40s, the physicists went to the Manhattan Project, even if they were doing other things. That was the place to be. And so now AI is the same thing, and basically said OpenAI is that place. So maybe we don't need a public sector organized Manhattan Project, but it can be OpenAI.
OpenAI is the Manhattan Project. I love that.
Yeah, well, maybe that's not a direct quote that we want to be taken out of context, but I think in terms of
the metaphorical Manhattan Project.
Yeah, in terms of scale and ambition, in terms of I think a lot of physicists would love to work at OpenAI for a lot of the same reasons that they probably were excited to. Well, okay, there's a number of different reasons. Maybe we'll just have to leave it as a nuanced thing rather than making broad claims.
Can we talk a little bit about this? Can we ever understand AI, especially as we go to these deep neural nets, or do you think it's a hopeless black box, so to speak?
Yeah, I think within this is my answer to the what are you a contrarian about? Although maybe on the internet everyone takes every side of every position, so it's hard to say you have a contrarian position. But I think within AI communities, I think my contrarian position is that we can really understand these systems, and in the physics systems are extremely complicated, and we have made a huge amount of progress in understanding them. I think these systems sit in the same framework. And another principle that Sho and I talk about it in our book, and that's a principle of physics, is that there's often extreme simplicity at very large scales, basically due to the statistical averaging, or more technically the central limit theorem. Things can simplify, and I'm not saying this is what happens exactly in large language models, of course not, but I do think that we can apply sort of the methods that we have, and also maybe hopefully have AI that can help us do this in the future. And by AI I mean tools, not like individual intelligences just running on their own and solving these problems. But I guess I feel at the extreme end that this is not going to be an art, that the science will catch up, and that it will be able to make extreme leaps in really understanding how these systems work and behave.
So Dan, we've talked a bunch about what physics can teach us about AI. Can we talk a bit about what AI can teach us about physics? Are you optimistic about domains like physics and math, and how these emerging models can probe further into those domains?
Yes, I'm definitely optimistic. I guess my my perspective is that math will be easier than physics, which maybe betrays the fact that I'm
you're
a
a
physicist,
physicist.
not a mathematician. And I'll say I can say I can give explain why I think that in a second. But I still have a lot of friends that work in physics, and they there's like a growing sense, and maybe even approaching a dread that, and maybe this is actually the answer to why do physicists work on AI, because if what you care about is the answer to your physics question and you want to make it happen as soon as possible, what is the highest leverage thing you can do? Maybe it's not work on the physics question you care about, but it's work on AI to make to because you think that the AI might end up solving those questions very rapidly anyway. And I don't know the extent that anyone really takes it seriously, but I think within the theoretical physics community that I come from, that this is sort of a thing that someone gets thrown around and discussed. I think maybe to give a more object level answer, I think what's exciting about math, and maybe when you have Noam Brown on, if you have him on, he'll talk about this, but this is something that he's talked about for a while before he joined OpenAI. I think that we have we made a lot of progress in terms of solving games by doing more than just looking up what is the strategy that we should use to play the games, but also being able to simulate forward. And the way that if I'm in a very hard position in a particular game, rather than just playing with intuition, I might sit and think about what I should do.
Yeah.
Sometimes this goes under the name inference time compute rather than training time compute or pre-training. And there's a sense in which what it means to do reasoning is very related to this ability to sit and think. So we know how to do it for games because there's a very clear winning and loss signal, so you can simulate ahead and sort of figure out what it means to do good or not. And I think math, in some parts of math, again, I'm not a mathematician, and always scared about talking about math publicly and saying something wrong that will upset mathematicians, but it seems like certain types of math problems are not as constrained as games, but are still constrained enough where there's a notion of, like finding a proof, right? There's different problems in terms of search, in terms of how do you figure out what is the next, move in the proof. But the fact that we might call it a move suggests that there's things in math that feel a lot like games. And so we might think that the fact that we can do well at games maybe means that we can do well at certain types of mathematical discovery.
Well, I was going to say, since you mentioned Noam, he likes to use the example with test time compute of whether it could help to prove the Riemann hypothesis.
Right.
Is there a similar problem or hypothesis in the world of physics that you are optimistic AI can help to solve sometime in our lifetimes?
Yeah, so I mean, there's a millennium problem relating to physics, and if I try to remember exactly what it is, I'm sure I will butcher it, and then no one will believe that I'm actually a physicist. But it's related to it's a mathematical physics question related to the Yang-Mills mass gap. And but I think what I wanted to say is that I think some of the flavor of what physicists care about in doing physics feels a little different. This is where I might get in trouble. It feels a little different than some of like the mathematical proof type things. Physicists are known to be more informal and hand wavy, but also on the other hand connected to in some sense connected to the interplay between experiment and the sort of models that physicists study is maybe what saves them, is that they have things that are informal and hand wavy but very explanatory. And then the mathematicians, it's like we were saying earlier, the engineers discovered all the exciting industrial machines, and then the physicists maybe cleaned up a bunch of the theory about how that works, and then the mathematicians come later and clean up, like formalize everything and clean it up even more. And so there's a mathematicians or mathematical physicists that clean up a lot of make proper and try and understand in informal ways some of the stuff that physicists do. But rather than talking about, I think the key point there is that the sort of questions that are interesting to physicists maybe don't look like proofs, but maybe they look like, and maybe it's not about how do we, given a particular model, how do we actually solve it? Like once things are set up correctly, like it's often, senior or, people that are trained in the field are able to sort of figure out how to analyze those systems. It's more the other stuff, like what is the right model to study? Does it capture the right sort of problems? Does this relate to the thing that you care about? What are the insights you should draw from it? And so for AI to help there, I think it would look different than the way we're sort of trying to build AI systems for math. So rather than here's the word problem, go and, solve this high school level problem, or, prove the Riemann hypothesis. It's like, the questions in physics are like, what is quantum gravity? What happens when something goes into a black hole? And that's not like, start generating tokens on that. Like, what does that even look like? And if you go to a physics department, people hang out at the blackboard, they chat about things, like maybe they sketch mathematical things, but there's a lot of other things that go into this. And so maybe the sort of data that you need to collect looks more like that, or maybe it looks like the random emails and conversations on Slack and the scratch work. And so, there are definitely tools that we can use, like help me understand this new paper so I don't spend 2 weeks trying to study it and understand it. Maybe let me ask questions about it. I think there are problems with the way that's currently implemented, but I think there are a lot of tools that will help accelerate physicists, just like Mathematica, which is a software package that does integrals, and it does a lot more than that. Sorry, Stephen Wolfram, but I use it to do integrals, and sometimes it doesn't know integrals, and you could look them up in like these integral tables, and anyway. I think there's and this applies to other branches of science too. Like I think the ways in which the questions are asked and what it means to do science in different fields maybe can look further and further from games, let's just say. And so to the extent that that's true, I think we'll need to, and not even clear that we'll need lots of ideas. We will need lots of ideas, but it's more just like I think we'll just have to approach them all differently, and maybe not like. Maybe eventually we'll have a universal thing that knows how to do all of it, but initially, like at least to me, a lot of these things feel a little different from each other.
You'll have a front row seat to it, in part because you're also on the prize committee for the AI Math Olympiad, which is something I'm personally super interested in. Maybe to your last point on kind of like maybe eventually this stuff generalizes, like why do you think people are so focused on solving the hardest problems today? Like physics, math, those were the subjects that everyone was terrified of in school, right? Where it feels like there's a lot more other domains that are also unsolved for now. Like, do you think going for the hardest domains first kind of lets you get towards a generalized intelligence? Like, how does solving these different domains kind of fit together in the grander puzzle?
Yeah, the first thing that comes to mind when you said that is to just push back and say, well, it's not hard. These are the easy domains. I'm bad at biology, but I can't. It doesn't make any sense to me at all. My girlfriend actually is bioengineering and in biotech, and so what she does just makes no sense to me. Can't understand any of it. Where physics makes complete sense to me. I think maybe a better answer, or a less global answer, is that like I was trying to say about math, there are constraints, and in particular with math, a lot of it is unembodied. You don't have to go and do experiments in the real world. They're sort of self-sufficient, and that's close to like what generating text, like the way language models work, or even the way some reinforcement learning systems work for games. And so I think the further that you go from that, the messier things become, the harder it probably is, and also the harder it is to get the right kind of data to train these systems. If you want to build a AI, and people are trying to do this, but it seems difficult. If you want to build an AI system that solves biology, I guess you need to also make sure robotics works, so that it can do those sorts of experiments, and like it has to understand that sort of data, or maybe it has humans do it. But there's a lot, for a self-sustaining AI biologist, it seems like there's a lot of things that are going to go into it. On the way we'll have things like AlphaFold 3, which just came out, and which I didn't get a chance to read the details of, but I saw that they're trying to use it for drug discovery, and so I think each of these fields will have things developed along the way, but I think the less constraints there are, and the sort of messier and more embodied it is, the harder it will be to accomplish. So,
no, that makes sense. So like hard for a human is not the same thing, doesn't correlate to hard for a machine.
Yeah. Plus, also maybe humans disagree about
Yeah,
what's hard
some of
or
us
not,
think more
but-
like machines, I guess. And then I guess the second question was like, do you think it all coalesces into like one big model that understands everything? Because right now it seems like there's a lot of domain-specific problem solving that's happening.
Yeah. I mean, the way things are going, it seems like the answers should be yes. It's really dangerous to speculate in this field because everything you say is wrong, usually much sooner
Good
than
thing
you
we're
would
on
think.
record. We'll hold you to it.
Yeah, exactly. But also, like, what does it mean to be different? Like, there's a trivial way to make both things, make the question meaningless by, like, you say the model is the union of all those other models, but there's also a sense in which mixture of experts was originally meant to be that. It's not that in practice at all. But, there's a sliding scale here. But, it does seem like people, at least the big labs, are going for the one big model and have a belief that that's, well, I don't know, but maybe I will in the future understand what the philosophy is there. Yeah.
Dan, we have a handful of more general questions to kind of close things out here. So I'll start with a high level one. If we think kind of short term, medium term, long term, and call it 5 months, 5 years, 5 decades, what are you most excited or optimistic about in the world of AI?
5 years ago I was after the transformer model came out, but it was around maybe when GPT-2 came out. So it seems like, for the last 5 years, we've been doing scaling. I imagine within the next 5 years, we'll see that scaling will terminate, and maybe it will terminate in, a utopia of some kind, that people are excited about, where we're all post-economic and so forth, and you'll have to shut down all your funds and, return monopoly money because money won't matter, or we'll see that we need lots of ideas. Maybe there will be another AI winter. I imagine that, and again, scary to really speculate, but I imagine like something will be interestingly different within 5 years about AI. And it might just be that AI is over and we're on to the next exciting investment opportunity, and everyone else will shift elsewhere. And I'm not saying that that's not what's motivating me about AI, but so maybe 5 years is enough time to see that. And I think in 1 year, or there's a 5. I messed this up. Whatever. Maybe it was 5 months. I don't remember. Sorry.
It's 5 months. It's okay. It's okay. These are approximations. I know you said physicists are very hand wavy. Venture capitalists are very hand wavy. These are approximations.
Yeah, in physics, I like to joke that there's like 3 numbers. There's 0, 1, and infinity, and those are the only numbers that matter. Things are either arbitrarily small, arbitrarily large, or about order 1. So okay, good. Thanks for reminding me. But yeah, for 5 months, I'm excited to learn what's exciting at the forefront of a huge research lab like OpenAI. And I think one thing that'll be interesting will be the delta between the next generation of models, right? Because there's ways in which things are scaling up in terms of, it's not really public, I guess, aside from Meta, but in terms of size of data, size of models, and we see scaling laws. And scaling laws, though, relate to something like the loss, and it's hard to translate that into actual capabilities. And so, what will it feel like to talk to the next generation model? What will it look like? Will it have a huge economic impact or not? And I think in terms of like estimating velocity, right? You need a few points. You can't just have 1 point. And we sort of have, we're starting to have that with GPT-3 to GPT-4. But, I feel like with the next delta, we'll get to really see what the velocity looks like and what it feels like going from model to model to model. And maybe I'll be able to make a better prediction in 5 months from now. But then I guess I probably won't be able to tell it to you guys.
Thanks, Dan. One thing that stood out to me is just like your writing is so accessible and light and funny, and that's not what I'm used to when I read super technical stuff. Like, do you think all technical writing should be informal and funny? Like, is that deliberate?
It's definitely deliberate. It goes into, I think in some sense, it's inherited. I definitely am a not serious person, but I also think it's inherited sort of from the style of the field that I came from. But I'll tell you a story. I was at lunch. I was a postdoc at the Institute for Advanced Study in Princeton, and I was having lunch and joking around with this professor, Nadi Seiberg, who's a professor at the Institute. And And then we got into, I think we're talking about, someone asked a question about like, what is a good title? And I was like, oh, the title has to be a joke. And he was on board with that. And then I was explaining that for me, the reason to write a paper is for the jokes. Like, you have a bunch of jokes in mind, and then you want people to read those jokes. And so you have to package it into the science product, and people want to read the science product, and they're forced to suffer through the jokes. And Nadi, he's this Israeli professor, and he was like, I don't get it. Why can't you just do the science? Why do you need the jokes are great too, but like, you should write for the science, not for the jokes. And I was adamant that I write for the jokes. But I think it's what you said, that at some point, you learn about the scientific method and the formal ways of doing things, and you learn all these rules, and then you grow up a bit. Or maybe I had a roommate who is a linguist. He's now a professor of linguistics at UT Austin, and like, he emphasized that he would tell me which rules that I could break, or where the rules come from and why they're important or not. And you sort of realize that you can break these rules, and like, the ultimate goal should be, is the reader going to read it and understand it and enjoy it? So you don't want to do things that compromise their ability to read and understand, but you don't want to obscure things. You want to make it, if it's more enjoyable, people are more likely to read it and take the point. It's also more fun if you're writing it. So I think that's where that comes from.
Dan, thank you so much for joining us today. We learned a lot. We enjoyed your jokes, and I hope you have a wonderful second to last day at Sequoia. Thank you for spending part of it with us. We really appreciate it.
Thanks. I was absolutely delighted to be here chatting with you guys. It was wonderful.